Some time ago, I built a very sturdy and rigid CNC milling machine out of ultra-high performance concrete, or UHPC. In this video, I will show the detailed steps how it was made, starting with a brief design overview and the specs, followed with the mold making, the milling of the parts, and the assembly of the machine and the enclosure, including the control cabinet. And if you want to see how well it performed, watch till the end. Hello and welcome to my channel. I started my CNC journey with a commercially available router kit from a well-known German company. However, I soon discovered that when milling metal, the overall concept, quality and performance did not meet my expectations. So I decided soon after to design and build my own concept. After a thorough study of possible designs and material choices, I went with a fixed gantry style router made out of UHPC. The CNC mill was made out of two massive concrete parts, the base plate and the fixed gantry. Each one weighs around 120 kilos. Normally, you anchor metal bars in the castings for the mounting surfaces of the linear rails and ball screw bearing housings. The complete casting with these bars is then milled on a larger machine to the required precision. Since I didn't have the possibility to have the castings milled, and it is extremely difficult to achieve flat mounting surfaces for linear rails directly in the casting with a wooden DIY mold, I decided to make for the X and Y axis a mounting plate out of aluminum, which has all the required features like flat mounting surfaces, parallel alignment edges, threads, recesses for the ball screw bearings, etc. already milled into the plate. These plates are then embedded in the UHPC. This concept is more effort, but it worked well and I was able to do everything by myself. The working principle of a fixed gantry router requires a moving bed. It is basically a mix of a traditional vertical milling machine and a moving gantry router. And it combines the best of both worlds. VMCs with a very sturdy Z-column have a lot of benefits in terms of rigidity, but they have the worst work area to footprint ratio because you need to have at least twice the size of your work area as footprint. Plus, in the Y direction, the depth of the Z-column needs to be added. And they have certain limitation in Y anyway, because your spindle center need to overhang at least the size of your Y travel. Routers with a moving gantry, in contrast, have a far better work area to footprint ratio, but at the cost of overall rigidity. CNC routers with a fixed gantry, however, achieve easily the rigidity of a VMC because of the massive gantry, but they build much smaller. And since I don't have infinitive space in my basement, this was the design direction to go. The work area was 600 by 400 by 200 millimeters, with an overall footprint of 1025 by 810 by 1200 millimeters. Total weight of the machine was 420 kilos. The axes were driven by 400 watt servos from Delta, the one on the Z-axis with an integrated brake. The spindle was originally a 2.2 kilowatt Mechatron, but I swapped this to a more powerful water-cooled Spindle GX30 with a 4 kilowatt 4-pole motor, 30k RPM and a SK30 ATC interface. The molds were made out of laminated plywood. For a one-off mold, wood is the right choice since it is relatively cheap and as well easy to work with. Even professional parts with small quantities are made in wooden molds. A key element of the mold making is to integrate all features of the finished casting already into the mold, like threaded inserts, plate for feet and anchor points, through holes and tubes for cable routing, vacuum channels, and so on. Since concrete is alkaline, it doesn't go well with aluminum. For that reason, I made the load-carrying parts out of steel. The parts for cable routing were mostly 3D prints. The design rules for machine beds out of UHPC are well documented. That includes as well the shape, size, and minimum distances of the threaded inserts. I turned more than 100 inserts out of hex bar stock manually on my lathe. That is not really a subject to amusement tax, and when I built my EpoxyGranite mill, I outsourced these parts. By the way, in case you haven't seen the video about that machine yet, I put a link in the description below. And in case you don't want to miss the upcoming videos about my next UHPC mill, give this video a thumbs up, subscribe to the channel and hit the notification bell. The reason why I made these special inserts, instead of just using a long hex nut with a bolt, is that the nuts have a much smaller surface area and as well a 30-degree chamfer. So when you just slightly over-torque the bolt, which fixed the nut temporarily to the mold during the casting process, there is a high risk that it is being pushed into the soft wood. And when that happens, it will sit prone of the casting after the molding, and that is something you definitely want to avoid. The inserts have a larger surface area and no chamfer and are less likely to be pushed into the wood. I milled the support blocks for the machine feet and as well the connecting plates between the gantry and the bases out of mild steel on the commercial router. This was a real challenge because the weak 2.2 kilowatt spindle required high speeds and feeds, but very small chip load. It worked, but it wasn't really fun. Also, the removed mill scale of the hot rolled steel made a lot of mess. Then I made some 3D prints for the internal cable routing and I could finally build the molds. The one for the bases was fairly straightforward since it is just a flat plate with a recess for the mounting plate for the linear components. The one for the gantry was far more complicated because of the C-shape, lots of chamfers and soft geometry changes, and overall more incorporated features. With hindsight, it would have been far easier to separate the beam from the side pillars, but hey, where would have been the challenge? On the first warmer day in mid-February, I casted the parts. UHPC is a concrete with a special cement called Nanodur from Dukerhof. It is very well documented and I link a few infos in the video description below. It can be mixed with all sorts of aggregates, but for machine beds, E45 and E80 are the right choices. E80 has a Young's modulus of 80 megapascal, which is even slightly higher than aluminium. The amount of water in the mix is extremely low and you need to add a superplasticizer to get it liquid. It cannot be mixed by hand and a free-fall drum mixer is essential. It takes about 30 to 40 minutes of mixing before all of a sudden the stuff gets liquid. And the temptation to add water during this period is high, but you must not do it. The benefit of the low water content, however, is that the shrinkage is below 1%. I even added a special agent to further reduce that to less than 0.5%. Another benefit of UHPC is that the stuff is self-compacting and self-bleeding, so no shaking is required. In contrast to regular concrete, UHPC cures relatively quickly and can be demolded already after a few days. It is in fact even advisable because the inserts are still fixed to the mold and even the little shrinkage there is can cause stress in the casting. The base plate came out really well and the top surface was almost impeccable. The demolding of the gantry, however, turned out to be a nightmare. I didn't plan for a proper disassembly and removal method of the plug that formed the C-shape, and on top it turned out that I demolded too soon. The concrete wasn't cured enough and I managed to introduce a crack in both rear corners. Normally this would have rendered the part as scrap, but I just wasn't ready to give up on it. Fortunately, both cracks were not too deep and went only from the backside to the large inserts for the cable routing. The structurally important front side was fine. So I waited a few more days until it was fully cured and went to the repair. UHPC bonds superbly to epoxy, which gave me several options. First of all, I removed with an angle grinder and a flapper disc all the excess cement and fine particle aggregates which rose to the top during the casting process. This left me with the pure concrete. Then I widened the crack a little bit and filled it with epoxy. After this, I remodeled the rear surface with a high-strength putty and several layers of glass fiber. And finally, I had 3 2mm thick steel plates lasered, which I epoxied to the part, one covering the entire backside. With this, I could save the gantry and it held up fine until today. Before I started the actual assembly, I finished the boards of the CNC controller, mainly because once assembled, the machine would have been in the way. I made 2 boards, a high voltage board with the VFDs for the spindle and the vacuum pump, and all the servo drivers. I added in total 6 drivers to have already a contingency for later additions like an ATZ magazine, a force or even a 5th axis. The second board contains the CNC controller from EpoxyCNC and a PC which runs the control software. I won't go into too many details here because I carried over the control boards to my mineral cast machine and I already covered them in my last video. Meanwhile, I noticed that the mounting surfaces for the aluminium machine beds were flat but not perfectly level. To be honest, I was rather disappointed in that because the fix was to level them with a special epoxy steel powder mix and a straight edge, what I really wanted to avoid. With hindsight, I could have done without the machine beds altogether with this method. Nevertheless, it worked well, and after sealing the castings with the 2K epoxy paint, I finally pushed them in place. I leveled the base plate by adjusting the feet, and once this was accurate enough for me, I pushed the 100 kg 20 heavy gantry in place with the help of a few clamps. The gantry side pillars have at the bottom steel plates casted into them, which rest on matching steel plates in the base. The gantry is fixed to the base with M8 bolts through both plates. The gantry plates have in addition a pattern of M12 threads for set screws, and the entire tramming of the gantry is done with them. With the main UHPC frame assembled, aligned and in place, I started with the machine beds out of aluminium. When you see the videos of the machining, you probably understand why I wanted to build a more robust machine in the first place. The bed for the gantry was in fact longer than the work area of my CNC router, but with some careful planning and literally hours spent on realigning, it was possible to make it in 2 steps with a 10 micron accuracy. For the linear components, I used for the first time bolt screws from TBI with a preloaded double nut with 0 backlash. The bearing housings are from SICK and the linear guides from Hyvin. Overall, this combo worked really great and I use this in all my builds now. As you may have seen earlier in the cut screenshots, I designed the gantry with sheet metal covers. This requires a split crossplate to fix the Z-axis. I milled the 2 parts out of mild steel to have a good rigidity because the contact area to the Z-axis is relatively small. I used the same design on my mineral cast machine again, but after several years of usage, my experience and conclusion is that it is not really worth it. The whole idea was to prevent chips piling up on the rails, and the design is rather useless for this. Once you achieve a certain material removal rate with high feeds and speeds and larger chips instead of dust, those chips fly everywhere. Trust me, everywhere. They pile up on the rails and are being pushed to the sides. The covers don't prevent that. What they do prevent, however, is that you see it in time to react and clean. So for my future builds, I will abandon this design again and rely on proper seals on the bearing blocks. The machining of the large bed of the Y-axis was relatively easy because it could be done in just one clamping. Lots of adaptive clearing for the pockets and plenty of threads, but nothing fancy. A moving bed design means that the rails and bolt screw are exposed to chips. But as you can see, this is a benchtop machine making use of every single millimeter of bench depth, so a cover was no real solution. Bellows are an absolute no-go with this type of design anyway, because they immediately get filled with chips and cannot compress properly anymore. The solution for linear blocks was relatively easy. Highwind offers a wide variety of add-on seals for all sorts of exposure, and I went with KK seals. And the bolt screw got a cover, but that required a special design of the nut housing. With this design, the bolt screw is completely protected from any chips falling down. But the C-shaped profile covers not only the bolt screw, but as well the servo and coupling, and overall this combination of cover and seals worked really well over the years. The last thing for the Y-axis to make was the large base plate, on which later on the fixture plate will go. I also added a little grease distribution system to do this from the front, because once the enclosure is up, the accessibility is not so great anymore. In this plate I additionally integrated a steel block for referencing, a vacuum port and as well the connection for a possible force axis. I will not go into too many details about the Z-axis. It was the first time that I have adopted this very sturdy box design for the fixed part of the axis, and the design overall proved to be so good that I used this in all my builds since then. The design evolved a little bit over time, but the basic principle remained the same. A very rigid box with fixed rails and a thick reinforced plate with moving blocks. I have explained the design and its benefits in detail in one of my earlier videos, which I link in the description below as well. And then I thought I have a very clever idea to incorporate a retractable 3D touch probe to the Z-axis. The mechanism worked really well, but the system was a clear fail. The machine was so rigid that I could easily run it with axis accelerations of more than 3 meters per square second. And what I noticed is that during very fast repetitive direction changes, like during a bore operation, the inertia of the relatively short stylus of the probe already caused it to trigger. That was not really an issue because first of all, EpoxyCNC ignores probe inputs during a running program, and I could also switch the probe on and off with the probing routine. But after like 9 to 12 months, I noticed that the triggering during probing became erratic and eventually failed completely. So when I changed the spindle to the bigger X30 and I had to redo the spindle plate anyway, I removed the probe again. When I did a post-mortem disassembly, I discovered that the constant hitting of the hardened contact balls to their corresponding cone in the PCB caused severe damage, making the electrical connection very unreliable. So if you want to adopt a similar approach, make sure to check the working principle of your probe first. And here are a few impressions from the completion of the machine and the build of the enclosure. I used the dead corner to house the entire control cabinet, including spindle, water cooling and pneumatics. I know that you normally shouldn't place them in the same compartment together with the electronics, but space is an issue in my workshop and there was plenty of room there. When I built the machine, I carried over the 2.2 kilowatt Mechatron spindle from the commercial router. But I always had issues with it regarding fretting on the ISO 20 tool holders and the cone. I had the pull-in forces changed twice, which improved the situation but never fully cured it. So when Spindle came out with their X30 spindle, I was one of the first guys to use it. And I do have to say that I never regretted this decision and even bought a second one for my new woodworking router. Now, let's have a look at how the mill performs with that spindle. Here in Germany, a so-called Star Challenge is quite popular among hobby CNC people. So, here we go. I have to say I was quite happy with that performance. But what do you think about it? Please leave a comment below. And if you watched the video until here, you can as well give it a thumbs up. It always helps with the algorithm. So, stay tuned and see you next.